this is the only action of the whole sequence. Because I have done transformations, and I am basically rotating about IKY, ILY to the whatever was the state of the operator before. For example, if sigma minus t was ikz, and to the equilibrium situation, I apply the sequence, I get ikz cos this plus ikzx ILY, and I get a 2-spin coherence. And this was the sequence for exciting double quantum coherences anyway. Yes, I used it in the multiple quantum coherence lectures. Okay. If on the other hand, my sigma t, my one before I apply the pulse for ikx, already I had applied a pulse and got my magnetization in the xy plane, and I apply this sequence, then I will get a ikx and a ikz ILY, which will be a coherence transform from spin k to spin L. And if sigma was iky, this sequence will do nothing to it. But this was not apparent if you just look at sigma is equal to iky and apply the sequence, it is not apparent that this sequence will do nothing to it. Okay, but you can break it down and make it a simpler one. These transformations also form a basis. Operators like ikx, ilx, iky, ilx, and ikz form subspace with rotation within the subspace. So if you just draw these subspaces, which is basically a subspace of spin k, where I have written ikx, iky, ikz, and multiplied by ilx and ilx here, then this forms a subspace. Here I have ikx, iky, ikz, and I multiply by y operator of L spin, and this forms a subspace. Or I can multiply it to x and z component, or with y to y and z component, and these form subspaces. And similarly, one can do it for spin L. And so the evolution under various different terms of the Hamiltonian of various operators can be even simply looked at with the use of this picture. If you have one of these terms which is causing evolution, and one of these terms which is what you want to look at. And so it's a compact way of getting the result. Since we are running out of time, I will skip some of this stuff. You can see that there is nothing special said here. This sequence x, y, y, where these two pulses have not the same phase but 90-degree phase shift, is a odd quantum excitation sequence that we discussed last time also. And the pulse with xx, the same phases here, is a even quantum excitation pulse sequence, and we have done that before also. If it's a heteronuclear spin system, this is the sequence which we use for inert, and one can simply calculate it through the density matrix procedure, and I will just give you the result. Please note there is a mistake here. Here it has to be a pi instead of a pi by 2. By mistake it's written pi by 2 there at this point. I hope you find it. And the result is interesting and is summarized on this point. At this point, that is the result of this sequence on a density operator is a pi evolution on the S operators, which is saying that it will focus the chemical shift of the S spin if it is there, or all S spin operators will change sign. Y and Z operators, S spin Y and Z operators, and you have evolution under JKL and JKM, and here you have a coupling between two I spins and a coupling of S spin to the I spins. So this evolution under the coupling of the I spins is given by this term, and the evolution with the S spin has this feature. It is a 2IKY SMZ. Okay, it's a SMZ and not Y there. Basically, we have not applied a 90-degree pulse to S spin, so there is no way to change SZ operator. Will remain there as it is. SZ operator cannot change. We have not applied a pulse, 90-degree pulse to S spins. I have tried to show here how we got from here to here by writing down the Hamiltonian here. This is not in your notes, but I don't think we have time to go through this at this point. So let's skip it. Oh, that's minor correction that earlier page numbers were wrong. It was page number 7, 8. And we already used COSY in lecture 4 in application. And I'll just go through application to the relay COSY in this now another 5 minutes. Although we don't have 5 minutes, but I'll go through this because this then illustrates what's going on. Okay. We are now going to calculate the result of this relay experiment. And the relay experiment is one in which we have K, L, and M spins, in which the K and L are coupled to each other, L and M are coupled to each other, but K is not coupled directly to M. In other words, JKM is equal to 0. And in the relay experiment, we finally get a cross peak from K to M. And this is how it works. Okay? We will directly go to the result of the calculation at point number 3. We know it's a COSY type of experiment at that point. Okay? And we are going to have antiphase magnetization from spin K to L. And that is the interface magnetization of spin L antiphase with respect to K. And it has a chemical shift and coupling KL, coupling dependence on this thing. This we already know from the COSY calculation, in fact. Okay? And so this is the result at point number 3. And now we just use the sequence tau, 180 tau, to calculate the result at point number 4. And this sequence says that we have to use this and this transformations. That is what I just mentioned before. Okay. The operation of the pi pulse about x-axis and k spin just changes the sign and nothing else. Okay, just changes the sign. K to kz by a pi rotation about x-axis goes to minus kz and does nothing to Ly operator. So this operation is taken care of by the sign change. This is given by, now we are having a on the kz it doesn't operate because it's a kz operator here, kz operator. So I can keep kz outside. Ly is good in change, so I get Ly cosine minus twice I Lx I kz sine. Okay. And there is another mistake. This 2 should not be there and this 2 should not be there. Oh yeah, no, it's not a mistake. My definition of tau is wrong. It's not tau by 2, tau by 2. The way I have written is tau, so it's 2 tau. Sorry. It is correct. Okay, already you see the problem. Whether I have defined tau by 2 here, then I should have only a single tau here. If a tau here, 2 tau, then it is correct. It's okay. Don't change the notes. Okay. All right. Then when we have JLM, and JLM is now going to, JLM has operators LZ, MZ. The difference from the heteronuclear here is that this pulse is, these are all homonuclear case. This is a homonuclear case. So I have now what I have done is I have first written down the evolution under first coupling, and now I must write the evolution under the second coupling. Under first coupling, that is KL coupling, this is what happens. Under LM coupling, this is what happens. So Ly changes to Ly and LXMZ, and this operator gives me another quantity here. There should be there is a square missing here. Please note down the square, and a minus sign missing here. Minus IKZ square. And since this is the term of interest, I'll go through it a bit slowly. So what we have is this term, twice IKL, the antiphase magnetization of spin L, antiphase with respect to K. And this is the one that I must evolve under the second coupling. The Z part of it commutes. So I can write IKZ outside. Okay. And I had another IKZ here. And this is one I forgot. Or maybe this one I forgot. Okay. So this is the quantity here. IKZ minus twice IKZ and this one here. So it will give me a half here. And then I have left with inside ILX, and ILX cos this, and ILY IMZ. Okay, this is straightforward because it is a rotation about z axis of an X operator, and it gives me X operator plus the antiphase magnetization with respect to the coupling operator. And this is the term which is of interest, which is saying that this is the one which will give us a L magnetization antiphase with respect to M. And it is the starting point of it was, if you remember, it was a K magnetization. And after I apply a 90-degree X pulse and get to point number 5, 90-degree X pulse, then I have this operator transforms to ILZ IMY. And this is the M magnetization antiphase with respect to L, which has a K frequency in T1 dimension and has amplitude which is dependent on the interval tau and the coupling constant JKL and coupling constant JLM. And this is what we had seen was for the relay experiment. But we had stated the relay result more or less in an ad hoc manner, but here we have calculated it in detail. And this is how you use the product operator formulas. All right. Thank you very much.